Energy is a very immense and broad topic. It includes looking at all of the changes of matter, both physical and chemical, that have associated energy changes with them. All of the processes that happen within biological cells and systems that require energy. Um, and the true nature of energy is studied through physics. So it totally runs the gamut of all of our sciences. So what we're going to do here is just touch on an introduction of what energy is. So first of all, we can think of energy as being a quantity that can be assigned to any particle, object, and system of objects as a consequence of the state of that particle, object, or system of objects. So this is our kind of classic definition of energy. But the idea is that you can take any particle and you can define any system and take a look at the energy that characterizes that system. Another way to think of energy, and again, this is a kind of strictly a physics definition, is that energy is the capacity to do work. And so then we might ask ourselves, well, what is work? Well, work is the process of moving an object. Now, this object could be as large as an ocean liner. It could be as small as a molecule of water in the ocean, or even an electron. But the idea is that if we're going to move an object, that we need to have energy in order to do that. And so energy is the capacity to do that, to move an object, to change its motion. And so we'll kind of start from that standpoint. There are several forms of energy that we're familiar with. Thermal energy, when we hold our hand up on a sunny day, we can feel the heat from the sun. We also, benefit from the radiant energy from the sun, the light energy, so we can see. So there's our radiant energy, our thermal energy. We're very familiar with the mechanical energy of things that are moving, so a car that's driving down the road. The electricity that we depend on day to day that comes from those little outlets in our homes is a form of energy. Sound is also a form of energy. And then the ones that we don't see normally day to day, nuclear energy, which is used to produce some of that electrical energy, and chemical energy, which we utilize every single day in all the processes that happen inside of our body. And so, but we need to become more familiar with those things. In addition to these forms of energy that we see on a day-to-day basis, there's also two general characteristics that we use to describe energy, and they are kinetic energy and potential energy. So kinetic energy is described as the energy of motion. Right? So any object that is in motion, any object or particle is in motion, we would say that it has kinetic energy. And then potential energy is based on the position of that object. So for instance, in the picture here, we have the bicycle at the top of a hill. So based on its position, if that bicycle were to go over the other side of that hill, as it is in the picture here, that potential energy, the energy of the position of the bicycle, would be transferred back into kinetic energy. So we have the bicycle rider riding up the hill, using kinetic energy to create more potential energy, and then riding down the other side, transferring that potential energy that he gained back into potential, or into kinetic. You would get the same type of thing if you were to stretch a rubber band. If you take a rubber band and you stretch it, you would be increasing the potential energy of that rubber band, and if you let go of it, that rubber band would shoot off, and the potential energy would be converted back to kinetic. In terms of kinetic energy, or excuse me, in terms of chemical energy, you might think of potential energy involving the position of, or the bonding arrangement of the atoms. So how those atoms happen to be bonded together would be, one case it could be at the top of the hill, and if those bonds then rearrange themselves so that they would be at a different position, different bonding, they could release energy. Same thing with the arrangement of electrons around an atom or a molecule. You could have the same type of situation where the electron were at a high potential and then it moved to a different place and it was at a lower potential and it would then release energy. Let's take a minute to look at our sources of energy. Here we have a diagram that shows basically most of our energy is coming from the sun. If we look up at the top of our list here, we use that light energy converted to electricity by photovoltaic cells. We have the light providing energy for photosynthesis in plants, and if we follow that through, those plants are then eaten by animals, and the animals, their wastes can then be used to produce Gobar gas. Forest fossilized to coal, and marine animals fossilized to produce crude oil and gas. We have the direct heat from the sun, and this can be used for heating, cooking, by use of solar heaters and solar cookers. The heat from the sun can also be used, or is used, to cause wind and tides and ocean waves, and this can then be used to produce other types of energy, such as wind energy and tidal or wave energy. And then finally, we have the heat from the sun that will cause evaporation of water from the surface of the earth, creating rain. That rain falls at higher altitudes, again, position, and that water then flows down, and that becomes then a source of hydroelectric energy. So these are all examples of what are called renewable resources, resources that, most of them are renewable resources. The block here in the middle, these would be referred to as non-renewable resources, from the sense that to regenerate these would take hundreds of thousands of years to generate more of that than what we have currently on the Earth. The transformative energy or conversion of energy from one form to another is going to allow us to do a number of things with the energy, which is what's most important. So you can take a minute to look through the 4 different examples that are given up here, and just take a look at the flow of the energy, for instance, in the brick being at a higher potential energy here, and as the brick starts to fall, the gravitational potential energy is getting converted to kinetic or mechanical energy of the brick falling, and then finally it's going to hit the floor. And when the brick hits the floor, you'd say, well, what type of energy has it been converted into? Well, the brick could make a loud noise, so you'd have sound energy. The brick could break apart, so you would actually be using some of the energy of the falling brick into breaking apart attractions within the brick. And of course, there's a possibility of some of the particles that the brick hits gaining kinetic energy, which is going to make them move faster and create some heat there. So again, you can pause the video and take a look at each of these different forms of energy conversion. All right, so hopefully you took a look at the 2 at the bottom here carefully. The one is with the use of hydrogen molecules and oxygen molecules. The rearrangement of those bonds, gives off an enormous amount of energy when they go from that type of bonding to the bonding that's involved in water molecules. That heats up the water molecules, releases a lot of energy there. From a biological standpoint, we have the sun providing energy to the leaves and the green plants. The chlorophyll molecule, the electrons in that molecule go to an excited state when energy from the sun is added to them, and that's the process of photosynthesis. You'll talk about more in biology. Now, in all of these transformations or conversions of energy, we have to keep in mind that we must always obey the first law of thermodynamics, which is that energy has to be conserved. In any of these transformations or conversions of energy, we cannot gain energy from the system. As a matter of fact, most of the time, energy is lost to some extent through friction and heat to the surroundings. So that's an important thing for us to remember, is that first law of thermodynamics, that anytime we convert energy from one form to another, we can't gain energy, and in most cases we actually lose a certain amount of energy. All right, and finally in this segment we're going to look at energy as a driving force in chemical and biological processes. There are two parts to this driving force in nature. One is called the enthalpy, and one is called the entropy. Enthalpy is a tendency to go towards minimum energy. So if you were to, say, put a ball at the top of a hill, the ball would roll down the hill, minimizing the energy. At the top of the hill, it has a lot of potential energy. It would roll down the hill and end up stopping at the bottom someplace, minimizing the energy of the ball. The second one that is a driving force in nature is entropy. All right, and entropy is the tendency of nature to maximize randomness. I'm sure most of you are familiar with this term, just with your bedroom at home. Things tend to get messy spontaneously, and in order to organize things, to make them less random, you have to put energy in. Now, a lot of times these two ideas will conflict with each other. So for instance, if you have an ice cube, if you have water in the solid state, the molecules of the water are in a highly organized pattern. They're basically put that way because of the hydrogen bonding that occurs between the different water molecules. However, and to break those apart, you have to add energy to water. But that does happen. If you put an ice cube out on the table, you will see that that ice cube will actually melt. Now, why does that melt? Because you're adding energy to the ice cube. You'd think that it should not do that. Well, obviously, by melting the ice cube, by having those bonds weakened and allowing the water to spread, to mix around, you are maximizing or you're increasing the randomness of the water molecules. So although you're adding energy to the water, you're making it more random. You're making the water molecules occur in a more random state. Now, obviously, it doesn't happen all the time. If you lower the temperature down below zero, now that ice cube would not melt. And so this is going to bring up, kind of an interesting thing that you'll deal with when you get more into the chemistry part of the energy, and that is, that one thing may dominate a process at one temperature, but if you change temperatures, that the other will dominate. But in general, the thing to remember now is that when you look at chemical and biological processes, they are driven by two things. One is a tendency of nature to increase the randomness of the matter, and the other is to minimize the energy. And then this brings us to the second law of thermodynamics, which is that the entropy of the universe increases with every change. The entropy of the universe increases with every change. So obviously with the ice cube melting, you can see that the order of the water molecules becomes more random. But what about in the freezing of ice cubes? How would an ice cube freeze? because obviously there you're making the water molecules more ordered by putting them together in the solid form. Well, in order to do that requires energy, and where that energy comes from is going to produce more randomness someplace else. So the universe is everything, right? So even though within a system we might actually be decreasing the entropy or making things more ordered, if you look at what it took to increase the order within a system, that actually decreased the order in the universe, or it made the universe more random.